It is Saturday the 1st of June 1974 and a 2-year-old caprolactam unit at the Flixborough Chemical Plant in Flixborough, England is being placed back into service. The installation has been somewhat of a disappointment for the site's operator, only being able to achieve full production at the beginning of the year. Its short service life has been plagued with issues and leaks, and just a few days before, it had been shut down due to a suspected leak. By the late afternoon, the site would be wiped off the face of the map in a massive and disastrous explosion. Many would be killed, many more would be injured, and millions of pounds worth of damage would lay in the explosion's wake. My name is John, and this is Plainly Difficult, and today we're looking at the Flixborough disaster. Flixborough village is in North Lincolnshire, England. Which is around here on a map. The sleepy village in 1938 will welcome a new neighbour, Nitrogen Fertilisers Limited. The company planned to use a 60-acre site for the production of ammonium nitrate, but just 26 years later, the area would be repurposed. Nitrogen Fertilisers Limited's parent company, Fission Limited, merged with Dutch State Mines to create a new company called Nipro Limited. This company was going to repurpose the site away from fertiliser production to the creation of caprolactam, an intermediate compound used in the manufacture of nylon. An initial unit of an output of around 20,000 tonnes per year was commissioned in 1967 using phenylhydrination, but the company sought out to increase its production. This would be via a cyclohexane oxidation process and would require Nipro to build a new plant on site, and this would be given the name Phase 2. It was completed in 1972, and the installation made use of a chain of 6 reactors. Whilst we're here, let's take a look at how the whole process ran. Each reactor was set 35 centimetres below the next inner line. This was to make use of good old gravity during the production process. Each reactor had a capacity of 45 cubic metres, were 5 metres high, and had a diameter of 3.5 metres. The walls consisted of 13mm of steel with 3mm on the inside made of stainless steel, and had 711mm diameter pipes with expansion bellows on each end to connect the 6 together in sequence. The oxidation process made use of all 6 reactors. Inside 25 cubic metres of cyclohexane is pressurised and heated to 155 degrees centigrade. The compressed air was injected and circulated via a perforated ramp inside the reactors in the presence of a catalyst. The liquid passed to each reactor via the pipework, and by the time it reached the outlet of the 6th reactor, around 6% of the cyclohexane had reacted. The remaining material was reprocessed, removing unwanted byproducts, and sent back through the reactors. The average flow through the system was 250 to 300 cubic metres per hour. To heat up the cyclohexane, a heat exchanger was used, and that employed steam. The steam flow to the exchanger is controlled by a valve, which can be controlled manually by the control room or automatically. To bypass the valve, a block valve is provided. This was closed on startup, meaning the only way to avoid overpressure is through the safety valves or manual intervention. During the reactions, some gas is given off, and this is routed back via an off-gas line to the heat exchanger and then to the atmosphere via a cooling tower, scrubber, absorber, and a flare. The off-gas lines serve to equalise pressure in all the reactors. Safety valves of each reactor was also provided, which would vent gas to the scrubber and flare, and this was set at 11 kilograms per centimetre squared. The new installation proved to be a little bit of a disappointment. with technical difficulties and leaks leading to lower than anticipated production levels. The lackluster production figures would further be hindered by the discovery of a cyclohexane leak around Reactor 5 on the 28th of March 1974. An investigation was undertaken the same evening and a crack was discovered in Reactor 5's thin steel wall. Management agreed to shut down and call off the installation for a more in-depth investigation in the morning. In the light of day, the situation must have felt like it was going from bad to catastrophe. A 6-foot crack was found in Reactor 5, and a manager's meeting was called to discuss what to do next. With production now completely halted, the management team brainstormed what the best way to restart production would look like. It was agreed that Reactor 5 be removed for inspection, but in lieu of a replacement, a bit of clever plumbing would be employed. Instead of Reactor 5, they would install an extended bypass pipe section to link reactors 4 and 6. This would make use of the already in situ 711mm pipe and bellows for the connections between 4 to 5 and 5 to 6, but be extended with a 500mm 20-inch welded pipes. Can you see the potential problem? Once completed, the installation would be able to resume production. A later Court of Inquiry report would point out 3 major concerns that weren't addressed. The first being that management still didn't know the cause of the crack. By not ascertaining what made it meant the same failure could repeat on the remaining 5 reactors. They were all pretty much the same after all. The second being that no one thought to inspect any of the other reactors for any similar failures in their steel structures. And finally, the third was that the new bypass line would have an inlet and outlet at significantly different heights to a fully working installation, as the drop between 4 and 6 was twice than that of other reactors. The calculation on the loads the new pipe could take showed it to be allowable. However, the dogleg part and its welds were not checked. This failed to meet British standards at the time and would be unallowable if inspected by a qualified engineer. You might ask, why use a 20-inch or 500mm pipe? Well, it was all they had on site. After Reactor 5 was removed, a scaffold was built around where the replacement pipe would go. Using nitrogen, the pipework was tested to 4 kilograms per centimetre squared. After no leaks were found, it was then tested to 9 kilograms per centimetre squared. Again, no leaks presented themselves. But like the whole design process, this testing stage failed to meet British standards, which would have required the pipework to be hydrostatically tested at a pressure of no less than 11 kilograms per centimetre squared, i.e. the pressure the safety valve was set to operate at. This meant that the pipework was never tested up to the maximum pressure that could be experienced by the system. Nipro pressed the installation back into work on the 1st of April. No leaks were detected, but no one in particular was keeping an eye on the homemade bypass line. Between the 1st of April and the 29th of May, the installation was used almost constantly, albeit for 2 occasions of a shutdown. Yet another leak was discovered on the 29th of May. This resulted in a shutdown, resulting in repair work being done on the 30th and 31st. After nitrogen pressure testing, the repaired section seemed leak-free. Restarting began on the 31st at 4 a.m, but just 1 hour later more leaks were discovered. After cooling down an inspection, these leaks seemed to have repaired themselves. Again, the reactors were started up and heat was applied. Pressure in reactor 1 rose too quickly and again leaks were discovered, requiring yet another shutdown. In the early hours of the 31st, the operators were confronted with a broken plant, and to add further frustration, the tools needed to repair it were locked away out of reach. But the reactors would be given the OK for restarting on the 1st of June. It's 7 a.m. and a new shift of operators are starting work. The time between the previous leaks and this team's book onto duty is pretty hazy. Even the official report states that the evidence with regard to the commencement of the shift is unsatisfactory. Multiple witness accounts contradict what state the plant was in, whether it was pressurized or not, but by around 8 AM, a reading of 8.5 kilograms per centimetre squared had been achieved, at a low temperature from nitrogen pressurization. The previous shift had reported a high pressure event requiring ventilation that took place in the early hours of the first, but not much else was thought about it. We also know that no leaks were found or at least reported. It was decided to begin the startup process by using steam into the heat exchanger to warm the installation up to 160 degrees Celsius at 9:30 AM. By 12 PM, the process control technician noticed the pressure at a point where intervention was required. Reducing the steam yielded no result. By now, the pressure was at 9.2 kilograms per centimetre squared. The technician sent an operator out to open the block valve. This did get the pressure below 8.8. The system was in a pretty difficult state. Even though its pressure was now satisfactory, the reduction in steam had reduced the vital temperature needed to start up. Although we will never know for certain, and that will become apparent shortly, it is likely the steam bypass line was opened to allow heating. But again, likely a whole new situation of high pressure requiring venting would present itself. Needless to say, the 1st of June was proving to be a difficult shift to get started. But their day would go from frustrating to fatal just a few hours later. At around 4:51 PM, the 20-inch 500mm bypass connection failed at its bellows, releasing upwards of 60 tons of cyclohexane. This came into contact with the reforming tower of the nearby hydrogen plant and ignition started. At 4:53 PM, an explosion felt up to 50 kilometres away enveloped the Flixborough plant. The flames set off secondary fires around the site, up to 100 metres tall. The control room, which housed most of the vital equipment for monitoring the reactors, was completely destroyed, taking with it 18 staff who worked within. Luckily, due to it being a weekend, fewer staff were actually on site, but the death toll was still significant, at 28, with an additional 36 injured and another 50 injured off-site by debris. For context, if the disaster happened on a Monday, around 500 people would have been on site. Over 2,000 buildings would receive varying amounts of damage, and the emergency response teams would be fighting the fire for over 2 days. An investigation would start quickly after the explosion, but one glaring problem immediately became apparent. Remember when I said about some of the parts of the chronology leading up to the explosion being a little bit hard to know for certain? Well, the explosion destroyed a lot of the valuable evidence and vital first-hand accounts of events in the last few moments. The difficulty would result in a bit of a headache for investigators, but nevertheless, the Court of Inquiry sat between September 1974 and February 1975 and examined physical and witness evidence. The report would be published later on in 1975 and would summarise the official theory of the disaster. The road to the explosion started with the removal of Reactor 5 and its subsequent replacement with the bypass assembly. The blame falls squarely at the feet of the assembly not being built and tested to relevant standards. Also, during the design of the dogleg assembly, which was done on the workshop floor no less, no one thought to consult the bellows manufacturer design guide, which would have specifically pointed out that it was not suitable for such an application. For nearly a month, the bypass section was pressurised and depressurised, weakening the section, to the point that the pressure and temperature used in day-to-day operation caused a rupture. I can show you in this demonstration. The more I bend the metal, the more it gets weak and will eventually fail. The report absolved blame of the control room staff on the day, as they had acted within the rules set out in relieving pressure when needed to. Also, the staff to manufacture the dogleg were absolved of blame, as they were simply building what they were told, and the workmanship of the welds was acceptable. There was, at the time, a contending theory. It was generally accepted that the 20-inch 500mm installation had failed, but the initiating events were argued to have come from an 8-inch pipe nearby, which after a gasket failing caused a fire, which then caused the explosion. Regardless, the blame falls on those who decided that this was the right route to take, instead of stopping production, investigating reactor 5 and then reinstalling. But there is another all too familiar factor to this event, and that is financial. You see, in the 1970s, the UK could only be described as a mess. The country was in the grips of a miners' strike. Because of the state of emergency enacted by the British government, industry was limited to just 3 days of electricity per week. In order to save energy, the agitators in the reactors were turned off. This, though, was just a cherry on the turd cake for Nipro, as the caprolactam plant had, for its short 2-year life, never reached the predicted levels of production, which by 1974 was severely financially straining the company. From a management perspective, the plant had to run to be able to try and claw back some money. Needless to say, we can put the blame of the disaster and inadequate Reactor 5 bypass down to financial pressures. Management were not against breaking the rules as well, as it was found to be holding far more chemicals on site than licensed to. Hundreds of thousands of gallons more, in fact. The company also undertook an internal investigation into the event and found that there had been several minor near misses involving on-site fabricated fixes. The disaster at Flixborough and disaster in Seveso, Italy in 1976, video available in the Plain Difficult archives, helped push through better awareness and laws regarding industrial safety. The plant at Flixborough, to much protest, was actually rebuilt and reopened, but Nipro UK ended up having to dig deep in their pockets in the aftermath. At least 6,000 public liability insurance claims were filed by 1975, costing around £24 million, roughly $150 million today. Now, where would you rate this disaster on my legacy and disaster scales? I'm going to say about a 6 for both. This is a Plain Difficult production. All videos on the channel are Creative Commons Attribution Share Alike licensed. Plain Difficult videos are produced by me, John, in a currently sunny corner of South London, UK. Help the channel grow by liking, commenting and subscribing. Check out my Twitter for all sorts of photos and odds and sods, as well as hints on future videos. I've got Patreon and YouTube membership as well, so check them out if you fancy supporting the channel financially. And all that's left to say is thank you for watching.